The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so the goal is to get a little bit of a sense of what do we do when molecules are not rigid. And the way I'm going to approach this is to show that there is, in fact, a serious problem that you would have encountered in 562. And you would have been wondering about how you deal with this. And then I'm going to see what we can do. So we're going to start with nuclear spins. And we're going to be talking about ortho-para states and nuclear statistical weights. And I will quickly go through the standard material from the elementary statistical mechanics course, where you end up seeing a rotational intensity alternation in homonuclear molecules. And we think we understand that beautifully. It seems to be a wonderful thing. And then I'll say, okay, suppose we go from hydrogen, which is 2 fermions, to acetylene, which is 2 fermions and 2 bosons. What do? All the simple ideas we had in 562 or whatever course you've seen this go out the window, because it's not possible to classify levels or to construct levels which satisfy the permutation symmetry for both hydrogens and carbons. So the next step will be to talk about symmetric double minimum problems, to show that when there are symmetric double minima, levels come in degenerate pairs. When the barrier is really high, the degeneracy is perfect, and one could almost think that only one level is there. This is the way around the problem. Whenever there are 2 or more identical species, the true degeneracy of the level can be 2. And this is how we get around the initial problem. So then I will start talking above my head about CMNPI group theory, but only very briefly, unless the questions, there are questions and they elicit some greater knowledge than I thought I had. Okay, so we start out with hydrogen, and hydrogen, we classify the nuclei of molecules according to whether they're bosons or fermions, and we ask about operations where nuclei, identical nuclei, not chemically identical, but identical, when they are permuted. And because you have identical particles, the wave function has to be odd with respect to permutation of fermions and even with respect to permutation of bosons. And if it's not even or odd with respect to all such permutations, you've written something which is not a legitimate wave function. So for hydrogen, we have 2 fermions, and the spin of each is 1/2, and so the total nuclear spin is either 0 or 1. Now it's required that the overall permutation symmetry, P12, for the wave function, the total wave function, has to be equal -1 times the wave function for fermions. The total wave function is a product of translation, rotation, vibration, electronic, and nuclear spin. I should have put nuclear spin earlier in the list. We don't ever have to worry about translation because all translational wave functions are symmetric with respect to permutation. For homonuclear diatomic molecules, we don't have to worry about vibrations. In fact, for all diatomic molecules, vibrations are totally symmetric. But this is not true for polyatomic molecules. But we're going to initially just talk about hydrogen and deuterium and oxygen and think we understand. And then I will introduce acetylene and we will realize we don't. Okay, so the electronic symmetry, the permutation symmetry, that's always a little puzzling. And I thought I would have an answer to that too with a nice picture. But I don't have an answer to this. I can only say that for diatomic molecules, states of sigma plus G and sigma minus U have positive permutation symmetry, and states of sigma U plus and sigma G minus. So these are positive and these are negative with respect to the permutation.
And that's only for diatomic molecules?
Well, that's the only thing I'm willing to say with authority, but I'd like to be able to say why this is true. And it would be nice to be able to say this with a diagram. And I thought I had it, but I don't. And so all I can do is assert this. This is important for being able to judge the permutation symmetry of polyatomic molecule electronic states and also vibrational states, especially when they're vibrational angular momentum. So, but this I can say is true. When you have doubly degenerate states, there's always one plus and one minus. So the critical thing is when there's no degeneracy. And so this is something that you can remember, and whether that helps you for other situations remains to be seen. Okay, so now for diatomic molecules, the permutation symmetry for psi rotation is -1 to the n. Not J, because N has to do with the total angular momentum exclusive of spin, and it's the nuclei that are being permuted in a rotation labeled by N. Now for singlets, N is the same thing as J. So that's just a subtle point. And so in the elementary statistical mechanics course, you're told this, and it seems reasonable. And so now, since everything else is pretty simple, in order to get the right symmetry, you have to pair the rotational wave function with the correct nuclear wave function. So if you have spin 1/2, then we have a mnemonic for writing the spin wave functions. We can write alpha 1, beta 2, plus or minus alpha 2, beta 1. And we can write alpha 1, alpha 2, and beta 1, beta 2. Okay, spin up, spin down. So permutation on this, positive. Permutation on this, positive. Permutation on the positive sign, positive. Permutation on the negative sign, negative. So what we have is 3 states where P12 psi nuclear is plus psi nuclear. And those are called triplet. Believe it or not, nuclear spin triplets. And one state where P12 where the nuclear spin is negative, and that's called nuclear spin singlet. For the triplet, I total is equal to 1. And for the singlet, I total is equal to 0. Again, big surprise, singlet and triplet. 2s plus 1 or 2i plus 1. Okay. So what about, all right, so for hydrogen, then, that means that we have, we need a state psi total, P12, is minus psi total. And so even J have even psi rot. So they must have odd nuclear spin, odd permutation symmetry nuclear. And so, well, so the even, I mean, the odd symmetry nuclear spin is the singlet. And so it has a nuclear degeneracy of 1. And the odd rotational levels will require an even symmetry psi nuclear. And those are the triplets. Nuclear spin equals 3. These are called ortho, and these are called para. And it's always true that the nuclear spin modification called ortho is the one with the higher nuclear spin degeneracy. There's more letters in ortho than para. You'll never forget it. I mean, it's really hard to remember, but you know, one little stupid mnemonic like that, and you can't forget it. I mean, para is like parallel, but that doesn't help. Unless you want to do something. So the one that has the higher nuclear spin statistical weight is always ortho. So for hydrogen, we have even J, odd J, and the even J have odd nuclear spin symmetry. The odd nuclear spin symmetry is singlet, and it has and is para. G nuclear spin equals 1, whereas the odd J have the opposite, ortho, G and S equals 3. So for the ground state of hydrogen, you have a singlet sigma G plus state, and the rotational levels 0, 1, 2. We can label them according to parity as well. And we can label them according to nuclear spin. And so this guy has a nuclear spin singlet. It's para. Another way of, and G equals. Okay, another way of remembering this is that it's always possible to make pure parahydrogen. And that's because using a catalyst, you can always convert all of the hydrogen to J equals 0. And this is also a good thing because J equals 0 has a degeneracy, rotational and nuclear, of 1, which means that you can make a perfect quantum solid because every particle in the solid is in the same state. And they're close together. And so it is an isotropic medium, bar none. And, so you've heard of parahydrogen. You can make orthohydrogen, but you can't make it pure. This you can make incredibly pure, and you can make an incredibly perfect quantum solid.
What do you mean by quantum solid?
Every particle is spherical. Every particle is in the same state, and they're close together. And so they know about each other. And so it's the best possible matrix that you can put something into, because the matrix is totally isotropic. And there's some wonderful matrix isolation spectroscopy on parahydrogen and also on orthohydrogen, but it's not quite so simple. Okay, so we have hydrogen. Next to hydrogen, we have deuterium. And deuterium, the nuclei have spin of 1. So the nuclei for deuterium are bosons instead of fermions. And so it turns out just the other way around. So for we can work this out, but what you can do is you can also describe the various nuclear spins of 1. Instead of alpha and beta, you can use 3 symbols, alpha, beta, and gamma, or whatever you want, and classify the states. And you can construct symmetric and antisymmetric states. And what you find is the states with I total equals 0 and 2 are symmetric. Is that right? That's right. And I total of 1 are antisymmetric. Total degeneracy 1 plus 5, 6, and 3. So here we have 1, 3, 1. For deuterium, we have 6, 6, 3, 6. So we have a 3-to-1 intensity alternation and a 1 to 2 intensity alternation. This state is ortho. And so you can, in principle, make pure ortho deuterium. But ortho has 2 values of the nuclear spin, total nuclear spin. One of them has I equals 0. The other one has I equals 2. So there are really 6 distinct quantum states associated with D2. And so even though you can completely cool all of the deuterium into J equals 0, it's not a good quantum solid because there's 6 states, and 0 and 2 are not even quite degenerate. Not a big deal. Okay, so this is all very simple, and people get very excited in 562 when they see this, and there is this incredible thing when you look at the spectrum of hydrogen and deuterium, you see an intensity alternation. This was not noticed first because the spectrum of hydrogen is in the vacuum ultraviolet, where there is, it might have been noticed in the Raman spectrum, but the killer was not hydrogen and deuterium, but the intensity alternation was first really understood and observed unambiguously in the spectrum of oxygen. And oxygen, the oxygen nuclei are bosons. The ground state of oxygen is singlet sigma G minus. So this classifies as odd. I covered it up somewhere. No, it's up there. So this is odd. And now we have bosons. And so we need an overall P12 psi total equals plus psi total. And so if the electronic wave function is odd, and there's no nuclear spins, the nuclear spin function is even. It has degeneracy of 1, and it's even. It's a singlet. It's ortho because There's only one. You can't have a para spin function for a pair of nuclei. Okay, it's ortho. And so in order for this to come out, you have to have, for the overall nuclear spin to come out to be positive, you can only have odd rotational levels. So you have an energy level diagram for oxygen, and we have 0, 1, 2. This is N. Remember, oxygen has a triplet sigma state, so there are going to be J sublevels of some of these. And this one doesn't exist. And this one doesn't exist. So we only have half of the rotational levels of oxygen existing. Okay. And so if you were going to look at a spectrum, an electronic spectrum, there isn't any other spectrum of oxygen, although there is a magnetic dipole allowed microwave spectrum. But those are transitions among the J levels associated with a given N. Because there's no state of even N in ordinary oxygen. Now, if you had oxygen 16, oxygen 18, then every level would be present. Now, one of the really wonderful things about this nuclear symmetry is that if you have an allowed transition, let's say you have a transition from the triplet sigma G minus ground state, you could have a transition to states that have U symmetry, and the only possible states are sigma U minus or triplet pi U. Well, in triplet sigma U minus, half the levels will be missing also. But this, you see a minus and a U, so this is an even state. And so what's going to happen is only the states with even N are present. Only states of odd N are present. And if you didn't know about nuclear spin, you'd know there's no Q branches here. And those are precisely the transitions that can't exist because of the nuclear spin. So one of the things that if you've forgotten some of the group theory or forgotten some stuff and you want to check, you say, okay, I'm interested in an allowed transition. I know from other less sophisticated stuff how to predict which are going to be the transitions that are allowed. A photon can't flip nuclear spins. And so the allowed transitions will be to the same nuclear spin species. Oxygen has nothing but ortho spins. And the excited state will have nothing but ortho spins, ortho states, rotational states. The states that are not, the transitions that are forbidden by simple rules are also forbidden because of the nuclear statistical weight rules. And so this is a way you can surprise people because you know something that's far more sophisticated than you're supposed to know, or that you can figure out in a short time. Because it's easier to know about rotational selection rules and that sort of stuff. Okay, so I've now lulled you into a sense of confidence that bring it on. I'll classify the levels and I'll tell you what are the nuclear statistical weights and which are going to be the existing levels and non-existing levels. And all I have to do now is write this molecule on the board and you will say, uh-oh, I don't know. Yes?
What if we were to do HD?
All the levels exist. All the levels have the same nuclear statistical weights. There's no permutation symmetry in HD because the protons and the deuterons are different. So you have a nuclear spin of 1 for the deuterium and a half for the hydrogen. And so you can have total nuclear spin of 3/2 and 1/2. And so the degeneracy for the 3/2 is 4, and for the 1/2 is 2. So every level will have a nuclear spin degeneracy of 6, and there's no intensity alternation or none. It's trivial. And that turns out to be a very useful thing because, for example, in the attempt to assign the spectra of a molecule with permutation symmetry, you're always going to have intensity alternation. But if you have an isotopically substituted molecule, you won't. And so there is an easy way. It's not foolproof because if you have a transition starting from an initial state, say k equals 2, where the asymmetry splitting is small, well, then you will also not resolve the nuclear spin species, and you will not see intensity alternation. But if you have fully resolved rotational transitions, the presence of intensity alternation is a unique sign you have a homonuclear, a molecule with symmetry. Okay, so we have 2 bosons, 2 fermions. What do? How do we write rotational levels that are classified, that have the right permutation symmetry? You permute 2 hydrogens, the overall wave function has to be odd. You permute the 2 carbons, the overall wave function has to be even. How can you do that? Because our naive idea is we rotate the molecule, odd J's are odd, even J's are even with respect to permutations, and you're sort of stuck. Do half the levels not exist because of oxygen analogy, or do half the levels have nuclear spin of 1, have a degeneracy of 1, and the other half have degeneracy of 3? These 2 possibilities are not compatible. So how do we resolve this? And the way we resolve this is we resort to something else that we know. What we know is about symmetric double minima potentials. Suppose we have a nice fat potential, and so here is V equals 0, V equals 1, V equals 2, V equals 3. And suppose now we either chop this in half or just put in a nice big barrier. Let's just put in a nice big barrier in the middle. Okay. Well, V equals 1 hardly sees the barrier. And V equals 4 hardly sees the barrier. 3 hardly sees the barrier.
Because it's 0 at the barrier?
Yeah. So half the levels are not very much affected by the barrier. And if we chop the potential in half, those levels would still exist, and the other levels would be blown into the stratosphere. They would no longer exist. If we said it was only a half potential. Okay. Remember something about that I told you probably, and that is you can tell the vibrational quantum number from the number of nodes. And so well, what's going to happen here? Well, suppose we draw the wave function. It's going to hit the barrier. It's clearly not going to work. It might tunnel through the barrier, but it can't possibly go to 0 at the other turning point. So how do you fix that? Well, if you raise this level, then it can start to be decreasing. And if you raise it more, you can, to this energy, you can get to the point where it's almost going to 0 when it gets to the barrier. And so what you do is you keep raising it so that it can tunnel without crossing 0, and you end up having a state that looks like that, instead of a state that looks like this. And they're at the same energy. Or depending on how big the barrier is, there'll be a small splitting. But the beautiful thing is when you approach it this way, you see that the node count is still the thing that tells you the order of the states. The lowest level will have no nodes, but it will happen to be almost perfectly degenerate with the next level that has one node. And the same thing happens here. This next state gets pushed up, and so what you end up having, instead of equally spaced levels, as you did without the barrier, you have levels which arrange themselves like this: 0, 1, 2, 3. And the spacing of these two is 2 omega y. Which is equal to 1 omega narrow. So if you took half the potential, you would have states that are separated by twice the frequency. And this is qualitatively reasonable. When you make a potential narrower, the levels get farther apart. When you make the potential half as wide, you might expect that the levels will get twice as far apart, although that requires using the WKB quantization condition to prove. You know about that. Okay, so.
Can I ask a question right now?
Yes.
So I understand the sort of idea that you can shift up this wave function, and it sort of has to end up looking like that to satisfy all the boundary conditions. I guess I don't understand what it is about. I mean, so I can imagine you have potential, and then you start putting a barrier in.
Yeah.
The barrier. Imagine you give a barrier that you continuously, bring up. So what is it about the barrier coming in that actually pushes the level up? That was just.
Well, there's many ways to answer that question. One is that the wave functions have to go to 0 at infinity. And so once they penetrate into the forbidden region, they have to have the right slope so that they can go to 0 at infinity. If they can't do that, they'll go to infinity at infinity. And so there's an exactly right slope that they have to have here. And so they have to fit. And so you know how to calculate a tunneling integral. You can propagate the wave function into the forbidden region. And so you just have to move it up. And so if you can't use up much action in here, then you have to pretty much go up to the level of the next higher state. And this gives you this wonderful picture that this and this are exactly degenerate, and that we normally think of this as an oscillator on the left, an oscillator on the right, and we can take linear combinations of them, and so we can have a local mode on the left and a local mode on the right, but those aren't eigenstates. The eigenstates have to respect the symmetry of the problem, and so the real states are these. But by taking sums and differences of these, you can have something on the left or something on the right. And that also says, well, if you have a big barrier, they don't know, nobody knows that there's anybody on this side. So what ends up happening is that when you have a large barrier between two symmetrically equivalent structures, you get two levels that are degenerate. They are degenerate, but they have different symmetry. And so for acetylene, if we label the levels H1, Ca, Cb, H2, well, there's another molecule, H1, Cb, Ca, H2. There are two identical structures. Two bonded networks, which are identical. And there are only two as far as I can figure out. And so that means that every level of acetylene is a symmetric and antisymmetric combination of these two bonded structures. And so they are going to have different symmetries according to plus and minus. And this is the answer to the problem. That if you write a wave function as the symmetric or antisymmetric combination of two bonded networks, you can write wave functions which satisfy the condition for boson or fermion, or boson and fermion, as you have in acetylene. And so what you find is that in the case of normal acetylene, every level is doubled, every rotational level is doubled. But in the case of acetylene, one doesn't exist. It has 0 statistical weight. And the other one has statistical weight of 3. Because that's what the hydrogens do for you. Or 1. One of them, I'm sorry, I said it wrong. One of the pair always doesn't exist. The other one of the pair has a statistical weight of either 3 or 1. So acetylene looks exactly like hydrogen. But what's hidden is there's really two levels. And when you have to do the group theory right, and all sorts of things, additional insights come out. But you know, superficially, acetylene treated as a linear molecule, a rigid, not vibrating linear molecule. It rotates like this, and the rotational levels are classified exactly the same way that the rotational levels of hydrogen are classified. And it just happens that one member of each tunneling pair, well, you could call it tunneling pair, each member of each degenerate pair, one of them is always absent. Which one is absent requires something that I had hoped that I could do for you. So anyway, this brings us to the formal tool that enables us to deal with identical particles in the same molecule. And it's called CMPI, Complete Nuclear Permutation Inversion Group Theory. And the beautiful thing about CMPI is that it's based on rigorous symmetries. Group theory that we all learn, point group theory, is based on a fiction. It's based on the idea that molecules are rigid and frozen at their equilibrium geometry. It's very powerful, and we've learned it, and we can do magical tricks with it, and all the tricks are right. But that's an accident. The rigorous symmetries are permutations of all identical atoms, all possible permutations of identical atoms, and inversion. Space inversion, not body inversion. So, and now here I'm starting to go beyond my current knowledge. Space inversion is not body inversion through the center of coordinates. Space inversion is like going from a right-handed to a left-handed laboratory frame. But this is something that I'm not so sure about, and I'd rather not say much, except that, you know, in the case of acetylene, where we're labeling the hydrogens as 1 and 2, and the carbons as A and B. So we would want to consider things like this. So these are obvious. These are permutations of the, I can never remember, the hydrogens. These are permutations of the carbons. And these are not feasible, because that would involve breaking 2 bonds. But there are legitimate questions. If we had a bag of atoms, that would be something that we'd care about. This is legitimate. So this is identity. This is end-over-end rotation, or it's equivalent to that. And these are the inversion times this operation. There are 8 of them. This group is called G8. The complete permutation inversion group for HF dimer, acetylene, vinylidene, anything that has 2 pairs of identical atoms is G8. It doesn't matter what the rigid structure is. And this is one of the beauties of it, because this is what enables you to go between states of one potential where you have one qualitative type of rigid structure and another potential where you have a different qualitative type of structure, because you don't care about the usual point group operations. You care about things that are rigorous and that have consequences in terms of the fundamental symmetry of bosons and fermions and stuff like that. So,
is it obvious that one can never have breaking 2 bonds at the same time?
well, you can actually. You know, well, suppose we start with this, and we go to okay. So we've taken one hydrogen around, made vinylidene, and then we take the other hydrogen back to where the first one came, and we've permuted. So we've used vinylidene as a transition state in the conversion of this to that. So yeah, you can have it. It just happens at very high energy. It just happens that we're really interested in it happening, because when this happens, it tells us that this is happening. We're really interested in this. We're not so interested in that. So when the tunneling through the barrier between this structure and that structure starts, it's because of a level of this that we want to know about. And CMNPI group theory is going to tell us how to get that information. In fact, whenever you start to have tunneling between qualitative structures, there will be a group theoretical signature of that. That I can say with confidence. What that signature is, I wish I could say, but I leave that to the smart people in the room rather than someone who can't learn anything anymore. Okay, so we have a group, and since there are 8 operations, there are 8 irreducible representations, all one-dimensional, so we need to classify all of the interesting things: electronic wave function, vibrational wave function, rotational wave function, nuclear spin functions, according to the irreducible representations of G8. Now there's two ways of labeling them. The old-fashioned way, which is reminiscent of ordinary point group symmetry, and then a different way where we have a symbol here which is either S or A, and a symbol here which is either lowercase s or lowercase a, and a symbol here plus and minus. 2 times 2 times 2, 8. So this is more useful label because it reminds you of what it's for, whereas here you have to sort of remember some stuff. And so, except I don't remember which is the capital letter and which is the lowercase letter, and I have written down somewhere. I hope. Yeah, here it is. So this is the carbons, and this is for the hydrogens, and this is parity. So we have 8 irreducible representations that can be labeled in this way. And our job is to put these irreducible representation labels onto the vibrations and rotations of the various isomers of acetylene. And the easy thing is vibrations. The hard thing is rotations. And I really did expect that I could do this, and I can't. But there is one thing that I can tell you, and that is when we talked about asymmetric tops or any kind of we had labels J, K, A, or KP, KC, or KO. And these labels are sufficient to map onto the 4 irreducible representations of the molecular rotation group. And Ka, Kc, even, 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 odd, odd, even, odd, odd. We factored the rotational Hamiltonian into 4 blocks. The 4 blocks had labels according to the odd or evenness of the Ka and Kc basis functions. There are no interblock matrix elements. And there is a 1-to-1 correspondence between these symbols and irreducible representation labels in G8. And that's where I can't act as your guide, because I thought I had it worked out, but every mnemonic I've used has inconsistency. So I would really suggest that you spend some time with this paper by Jim Lundberg, which I find, at the time when he wrote it, I thought it was wonderful because I thought I understood. But it's not wonderful enough because I can't get an understanding of the subject to lecture to you from this paper. This paper is from my Highland dyes and my stimulated emission pumping book. I do not have it electronically, but I do have copies that I can give you. Who would like such? Well, you can just come to my office and get a copy. If there's only one person who wants a copy, how many people want copies? Okay, I have some copies. I did some Xeroxing, and there's a little cutoff on the edge. And that's Susan. And I'm not going to answer that. It is. She should know that I'm lecturing at this time. Is it after 6? What?
It's two minutes up.
Well, she's just going to have to wait till I finish. Anyway, so I have some copies in my office. And there it is. Where do I want to leave this? Oh, well, I have evaluation forms. And so I'd appreciate if you would say some nice things about me on these, because nobody ever, I always get these terrible evaluations. And, and so we can hand them in. Annalise will take responsibility. responsibility for them at some point. You can give them to her in the office or whatever, but she will take responsibility. Okay, so there will be no more lectures in this course. And everybody who's registered for the course is going to get an A. And that's that. That's the end. I wish I could give this course again, and I wish I could kill this topic, especially because of Adam, who came to hear me convey insight on a subject which is difficult, and I have disappointed him as well as the rest of you. But it is a beautiful subject, and we will understand it all together, or some of us together. Okay, thank you for coming to my lectures, and I wish we could go on.